Today I also discuss one important topics, obviously related to linear algebra, especially algebra. We also discuss maximal, okay, maximal linearly independent subset, maximal linearly independent, okay, subset. Today we discuss this topics. This one is an important topic, I think. Now, in previous class, we also discussed familiar dimension and basis of a subspace or a vector space. Okay, so today we also start from definition. One definition, we start from that. Okay, let A be a family of set. Let A be a family of sets. Okay, let A be a family of sets. A member M of A. A member M of A. Okay, a member M of A is called maximal. Is called maximal. Okay, with respect to the set inclusion. With respect to set inclusion. With respect to set inclusion. Okay, if M is contained, if M is contained, okay, in no member of F, in no member of F, okay, other than M itself, other than M itself. Understood? That means let F be a family of set. A member M of F is called maximal if M is contained no member of F other than M itself. Understood? Then we also, that means discussion one important example related to that. Okay, so one example we that will discuss now. Let A be A be the family of subset. A be the family of all subsets, okay, of a non-empty set is, of a non-empty set is, okay. Then what happened? This family F is called power set of S. This family F is called the power set of S. The power set of S. Okay. Then what happened? Then the set S is easily seen to be a maximal element of F. The set S is easily seen, okay, to be a maximal element, to be a maximal element, okay, of this script F. Understood? That means this one example of maximal set. Okay, that means we also discuss this. If F be the family of set, then a member M is called maximal if M is contained no member of F other than M itself. Okay, let if F be the family of all subsets of a non-empty set S, then the set S is easily seen to be a maximal element of F. That means no subset of S obviously contain S. Okay, so this one that means be a mm, maximal element of this scripted. Okay, so we also is that person and going to discussion of another example. Okay, so it is that person and going to discussion on another example. This example is that means let S and T be two disjoint set, be two disjoint sets. Okay, S and T be two disjoint set. Obviously S and T both are non-empty. Okay, then what happened? Then obviously let A be the union of their power sets. Okay, let A let A be the union of their power sets. Okay, of their power sets. We know about that power sets. That means P of S or P of T. Then obviously all subsets is contained in this set. Okay. So then what happened? Then S and T are both maximal element of F. Okay. Then S and T are both maximal element in this F. That means S T are two disjoint set. That means S intersection T equal to phi. Then we also that means take some power set. That means this family equal to union of P of S equal to P of T. Okay, that means all subset of S and all subset of T obviously contain this collection of sets. Okay, F. Then what happened? Then S obviously maximal element in F and T obviously maximal element in F. Because we'll see about that. Here S, then no subset is here contain S. Okay, and obviously T, no subset is in this collection is contain T. Okay, so this S and T are both maximal element. Okay, if S union T is here, then this one is maximal element. Okay, but S union T is not here, so this one is, that means this S and T are both maximal element in this collection. Understood? Then we also, that means going to another example. Okay, we write it in then star, and now we write another example related to this maximal element of some collection. Okay, or a maximal member. So we erase that portion and going to another example, discuss another example. Okay, so here we talk about that let this script F, okay, be the family of all subsets. Okay, be the family of all subsets of an infinite set is. Okay, then what happened? Then F has no maximal element. Then this F has no maximal element. Understood? Then F has no maximal element. Okay, now also that means going to another option. Okay, if M is any member of F, or if M is any member of if, okay, and s is any element of s, and s is sorry, this small s, okay, small s, be any member, small s is any element of this set is any element of set is, okay. Then what happened? That is not in m, that is not in m. Then what happened? Then obviously m union is, okay, m union, the singleton is a member of f, is a member of this script f, okay. Then what happened? That means that contains m as a proper, that contains m as a proper subset, okay. So that means in for this cause, this one f has no maximal element, understood. Then we also discussion another example, chain, okay. Discussion another definition, okay, chain. So we have no need to discussion another example to understand this maximal element or maximal member of some collection of set, okay. So now we're going to discussion of another example, okay. So we write here definition, okay. Then what happened? A collection of set, a collection of sets, okay, a collection of sets C is called a chain, okay, a chain or nest or tower if for each pair of sets, if for each pair of sets, okay, A and B in C, A and B in C, okay, either a subset of B, either a subset of B or B subset of A, understood. That means a collection of sets C is called a chain, okay. When if for each pair of sets A, B in C, either a subset of B or B subset of A, this one happen, okay. Then we give some example related to that topics, okay. Here that means for any positive n belongs to z plus positive integer and a n equal to 1 2 dot 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 n, okay. Then the collection of sets, then the collection of sets, collection of sets, this script C equal to an, here n equal to 1 2 3 dot dot dot, okay, is a chain, is a chain, understood. Then what happened? That means in this way am subset of an, am subset of an, okay, if and only if and only if am less than equal to n, okay. That means this one happen, an equal to 1 2 dot 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 dot. That means a1 equal to 1, a2 equal to 1 2. In this way, that means am subset of an equal depend only n m less than equal to n. So this one clearly, that means satisfied mm, the relation of chain. Okay, that means this one be a chain. Okay, so this collection be a chain. Now we also discussion maximal principle. Okay, so it is that portion, and obviously that means discuss this maximal principle. Here we write maximal principle. Okay, and we also state this one now. Let A be a family of sets. Let script A be a family of sets. Okay, if for each chain, if for each chain, if for each chain the script C subset of the script F. Okay, there exists a member of F. There exists a member of F. A member of F. Okay, that contains each member of script C. That contains, okay, each member of script C contains each member of script C. Okay, then F contains a maximal, then the script F contains a maximal member, a maximal member. Understood? Okay, that script F a family of sets. If for each chain C subset of F there exists a member of the script F that contains each member of C. Okay, that means a member obviously contain each member of C, then the script F contains a maximal member. Okay, that means for each chain, okay, for each chain C subset of this script F there exists a member that contains each member of this chain. Okay, that means for each chain, that means this family of sets have chains. Okay, and in each chain obviously one, that means member obviously contains an other members, then F contains a maximal member. Okay, understood? Then we also discussion one important definition. Okay, related to that topics, we again we erase that portion. We also discuss maximal linearly independent subset. Okay, we erase that portion. Here we write definition. Okay, here we write definition. Then let S be a subset of, let S be a subset of a vector space V, of a vector space V. Okay, a maximal linearly independent subset, a maximal linearly independent subset. Okay, a maximal linearly independent subset of S is a subset B of S, is a subset B of S, okay, satisfying both of the following conditions. Satisfying both of the following conditions, okay. First one, B is linearly independent. B is linearly independent. And P, second one, okay, the only linearly independent subset of is the only linearly independent subset of is, okay, that contains B is B itself. Understood? That means B is linearly independent, okay, and the only linearly independent subset of S that contains B is B itself, okay. So then we also call this B is a maximal linearly independent subset, okay. Now we are also going to discuss another example, okay, related to that topics. Then we erase that portion and going to discuss one important topics. Another example, okay. We write it here, example, okay. Then what happened? That means here we write x cube difference 2x square difference 5x difference 3, okay, and 3x cube difference 5x square difference 4x difference 9 is a maximal linearly independent subset. Maximal linearly independent subset of S equal to here 2x cube difference 2x square, okay, plus 12x difference 6, here x cube difference 2x square difference 5x difference 3, okay, and 3x cube here difference 5x square and difference 4x difference 9, okay. Then this one, that means is a maximal linearly subset of S, okay, in P2R. That means this set is linearly independent, and obviously the only linearly independent subset of is that contains this set, okay, obviously this set itself. So this one is a maximal linearly independent subset, okay. So now we are going to one conclusion, okay. So we write it here. That means a basis beta for a vector space V is a maximal is a maximal linearly independent subset. Maximal linearly independent subset, okay, of V. A basis beta for a vector space V is a maximal linearly independent subset of V, okay, because I write it here, because, okay, first one, beta is linearly independent. Beta is since basis then linearly independent, okay. That means a basis is a maximal linearly independent subset. Why beta is linearly independent? And again we write it here, second option, if V belongs to V, okay, if V belongs to this vector space and V does not belongs to this beta, then what happened? Then beta union V, okay, is linearly dependent, is linearly dependent, linearly dependent, understood? Dependent, okay. So that means this one, so we talk about that. A basis is a maximal linearly independent subset, understood? So we now erase that portion and going to further discussion of that one theorem. We also discussed one theorem now, okay. So we erase that portion and going to further discussion of that. We write here theorem, okay. Let V be a vector space, let V be a vector space, okay, and is a subset that generates V, and is a subset that generates V, that generates V, okay. If beta is a maximal linearly independent subset, if beta is a maximal linearly independent subset, okay, if beta is a maximal linearly independent subset of S, okay, then what happened? Then beta is a basis, then beta is a basis for V, understood? That means V is a vector space, S be a subset that generates V, and beta is a maximal linearly independent subset of S, then beta is a basis, okay. We're going to prove of that. What happened? Let beta be a maximal linearly independent subset of S, maximal linearly independent subset of S, okay. Now because beta is linearly independent, beta is linearly independent, okay, then it suffices to prove that, it suffices to prove that, okay, to prove that beta generates V, okay, understood? Then beta be a basis, not a problem at all. Now we claim a subset of span of beta. Okay, a subset span of beta. For otherwise, okay, for otherwise for otherwise there exists a v belongs to S such that v does not belong to span of beta. Okay, now obviously beta union v is linearly that means independent. Okay, if beta does not belong to span of v, then what happen? Then we talk about that beta union v be linearly independent. Okay, beta union v be linearly independent. Understood? Then what happened? That means we have contradict the maximality of beta. We erase our portion and going to discussion of that. Okay, then we have contradict the maximality of beta. Understood? Then what happened? Then therefore a subset of span of beta. Okay, because span of is equal to v, okay, then we also show that. Okay, then obviously that means span of beta equal to v, okay, that means a subset of span of beta, then span of beta equal to v, since span of is equal to v. So we also prove this theorem. Obviously this theorem says that means a subset that is a subset that generates v, then obviously beta is a maximal linearly independent subset of S, then beta is a basis for v. Okay, so today I stop here. If you get this type of video, please subscribe my channel. If you give like, please click on like options. If you have any comments, suggestions and questions, write it in comment box. So today I stop here. Thank you.